Hello everyone. Welcome to the problem solving session, week 7 of the course on computational complexity. So, the topics for today would be some basics of circuits and the parameters that we defined earlier, the size, depth, and so on. We'll also look at some specific types of circuits. Those are called monotone circuits. Then you have AC0 and C0. So we'll define them as and when we come across the questions. So just to recall, a circuit is a DAG where you have nodes like these, and and the leaves are the inputs for us, and all the other gates excluding the leaves, those are called the internal nodes, are labeled with gates. And we saw that and or negation, this is one standard basis that we typically work with. So you can assume that these are labeled with these gates, and the gate at the root is what we say is the output, computes the output of the function. So that's how we define circuits. And the longest path from the root to the leaf is what we call the depth, and the total number of gates that are there in this circuit is what we call the size. Okay, so we know that circuits are universal model of computation, that is for any function that we can imagine, any Boolean function, there is a corresponding circuit C. That computes F, and one such circuit that we know is CNF TNF. This is something we can trivially come up with, but we are not happy with this because we also want the circuits to be small in size. So we ideally want circuits to be poly-sized. Okay, so okay.
But I have a query at this point regarding the universal model of the computation, because I read this thing in the notes that the number of the Boolean functions would be pretty large. Say with n number of the inputs, there would be 2 raised to the power n number of the total Boolean functions possible. And however, the number of the possible circuitries would be, say, or 2 raised to the power of the order of polynomial of n, and then the log of the polynomial of n. So since there is a difference in between the counts of the possible Boolean functions and the circuitries, so how is that possible that for every Boolean function we have a circuit available?
Yeah, so you're right. So in fact, we know that although this is something we would ideally want, we do know that this is not possible by the counting argument. So there are exponentially many functions that are there, like you said, but if you look at the total number of circuits that can be there of poly-size, then that is I mean exponential in uh, yeah n. So by simple counting argument, we know that this is not possible. So there are functions that are hard, that is they require explicit sorry they require large circuits, right?
Yes, but so when we say that this is the universal model of the computation, so what is the similarity in between calling something a universal model of the computation and something which is Turing complete? So are they same or the different one? And when do we call that okay, this model of the computation is the universal one?
Okay, so when we say universal, all we mean is that it is computable. That is, any function that you can imagine has a corresponding machine or model that you are working with. So, for example, for um, um, any function that I can write here, you know that there is going to be a circuit. It may be a very large circuit, but there is going to be a circuit, so it is computable in that sense. So we are not worried about the complexity at the moment.
Oh, I see. And then what about this term Turing complete? We often used to say that this is Turing complete. Like say there are different models of the computation. Probably the Turing machine is not the only one. There used to be some lambda
Lambda
calculus.
calculus,
Yeah.
yeah.
Yes. And then there is cellular automata, and now this circuit thing. So when do we say that okay, this is universal model of the computation, and are they equivalent of one another? So what is the situation?
um, so okay, so um, okay, so what we mean is that any um, language, uh, so we have this equivalence between languages and the Turing machine model,
Yes.
right? So this is okay, so this is the same thing that we know that languages are equivalent to the Turing machines. That is, for every language there is a Turing machine M, and it may not be deterministic polynomial time. We're not promising that, but there is a machine.
Yes.
Okay, and similarly, we saw in the beginning, like I guess one or two lectures earlier, that Turing machines and circuits are equivalent in terms of computation, in the sense that you can think of language as we wrote this as union of um,
Yes. We wrote it like this, yeah.
yeah, and then for each of them we had a function, or a circuit. So I'll call it C0, C1, and so on. So we don't have one circuit, but we have a family of circuits which will work with.
Yes.
Okay, so yeah, so that means that for every language, if you can have that particular model computing that language, then we'll say that it is universal.
But then what is the length of the longest string in such a language? Like you don't say it will continue forever,
Hmm.
say till infinite, and we do not know, I mean, till what extent will it continue? So then can we have such a circuitry having, say, the size of I mean, this infinite kind of
Hmm.
improving?
Yeah.
So is this justifiable?
Hmm. Okay. So when we say that we have this collection of circuits, where we only want the description, right? For example, even for the machine, we are not actually going to run it. You only want the description of the machine, right?
Yes.
So it is enough to um, show that there enough to just give the description of the circuit. So for example, um, if the function is let's say a simple function, that if it's computing and of n, so it could be that there's only one variable or two variables and so on. So this itself we can think of n having different values. So I don't need to give all the circuits. I just know that there's a description where you can have an AND gate with those many those many
Yes.
inputs.
Yes. It
So
makes sense. Yeah.
even if we can give a description, it is enough. You
Yes. I understood that. Thanks.
Okay, so hmm. Okay, so similar to the hierarchy that we had in the Turing machine model, we can think of restricting our circuits with respect to the depth and size parameters. So let's say I allow my circuits to have depth of order 1. Okay, there's another parameter. Let's say um, fan in is bounded. So let's say all of them have a fan in, all the gates have a fan in of 2 or at most 2. Then okay, I'll not talk about the size then. Okay, so we'll see why it is okay to assume that it is 2. Then so if I say that if I look at the circuits that have a depth of constant and all the gates have a fan in of 2, then it cannot compute all the functions, of course, by the same counting argument, that there are very finitely many or limited number of circuits that have um, that satisfy these parameters. In fact, we can count and it's going to be a very small number. So we'll look at these functions that can be computed by circuits of uh, constant depth and bounded fan-in. These are called NC0 functions, where okay, again the basis, if we don't specify anything, the basis is always and or negation. So this is the next class where the 0 tells you that it's a constant depth circuit. If I allow it to be log n depth and fan-in is still bounded, then we call it NC1. So these powers in general are um, yeah other parts of the log with respect to the log. Okay, so
Uh, yes, and what about the size of? I mean, how many different gates can I use? Like say in NC1, the
hmm.
depth could be the log n, and the maximum fan-in would mean the number of the inputs, I guess. Number
um,
of the inputs, or something else.
yeah, for every gate, how many incoming
Uh,
arrows?
oh, okay, okay, yes. So then, yeah. So what is the what? I mean, how many different gates could be there in NC1?
In all of them, we will always talk about uh, and or negation gates. So are you saying?
I mean, their count. Can we have, say, a very large number of gates possible,
Oh,
and
okay.
oh,
Mm-hmm.
and with the depth of the log n?
Okay, okay, okay. Got it. So, okay. So if we look at the, um, so this is similar to our um, binary tree, but it's not exactly a tree. So we'll count all the DAGs that can be there. So if the depth is, I'll call it D for now. We will later substitute it to P log n. So okay. Mm, hmm. Okay. So what is the maximum number of gates that can be there in this case? So I think that would be when it's a tree, right? Because we are not reusing the uh,
Yes, complete binary
complete
tree. When it is
binary tree.
complete binary tree.
Okay, and at every step we are doubling the number of gates. So initially here we had one gate. At the second level we have two gates. Then it becomes 2 square. Then it becomes 2 to the 3, and so on. And at the final level, let's say we have 2 to the d. So
Yes.
so the total number of gates that we have is something like 2 to the d plus 1 minus 1, or let's say order 2 to the d plus 1. But d for us in this case is log n, so this will be poly-sized, so like
Order of, yeah.
order of, yeah.
Not, yeah, because D is of the order of, yeah, of the order of eight, right? Yeah. Yes.
So actually this will become polynomial sized, because if this is 2 to the c log n, then this will be n to the c.
Yes, 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 right.
Okay. Hmm. and we know that NC0, I mean,
And here N has nothing to do with non-determinism or any kind of
hmm,
determinism. This stands for some Nick you said in class.
stands for
Nick's
Nick's
class you
class.
said.
Yeah.
Okay. And as far as the circuits are concerned, I mean, there is no rule of determinism and non-determinism. This is the case.
Hmm.
And we
Yeah.
will never talk about it in those contexts. Okay.
Yeah. Okay. So, huh. So these are, I mean, so one variant that you can think of is, instead of allowing the fan-in to be constant, if you make it unbounded. So if you make it unbounded and the depth is the same, then we call it AC0 class. And similarly, we can define unbounded fan-in but logarithmic depth to be AC1, and so on. So we get a whole hierarchy of classes. So um, clearly NC, and so on. So this continues, and here we have AC0, AC1, and so on. Okay.
I have a question here that so if the unbounded values are allowed, then why would I go for the AC1 or the AC2 as the first place? I would prefer to work with the constant height only, and then I will include all the inputs, give all the inputs to I mean, to the circuitry at the level one only.
Mm, uh, okay. So sometimes okay, so sometimes there are results of the kind that. Okay, so let me understand the question first. So, are you saying that if I'm allowed unbounded fan-in, then why would we work with the NC class? Is that.
No, no, no. If unbounded finance are allowed, then why would I go up in the hierarchy of the AC class only? Why would I
Oh,
go
okay,
till the
okay, okay.
level of the log n?
Oh, okay, okay. So, okay, so you're saying why, I mean, why is AC2 more powerful than AC1 or some.
Yes, yes, that's what I mean
Okay, okay.
exactly.
Sorry. Yeah. Okay. So, okay. Mm, okay, so how do we show that? Okay, let me think about it. Hmm. Okay. Okay. So, okay. So notice that when we have this depth thing here, the number of gates that we were still allowed. Um, okay. Let's not. I mean, put the arrows right now, because it could be taking any subset of these arrows. But the number of gates that I can still have is. Mm,
So this would be a tree and whose height is very low, but then a node can have as many, I mean, many children. Uh,
Yeah,
that would be.
but the number of inputs that you have is still n. So at some point you will be repeating the, um, I mean, the configuration. So some nodes will become redundant. So um, I don't know if it is easier to see this if we go back. I mean, bottom up. Um,
So
hmm.
can there be a case that I divide n number of the inputs into say four chunks, and then I use my AC kind of the circuitry for the first chunk. I get some result, and then AC kind of the circuitry, AC0 kind of the circuitry for the second chunk, and similarly I use AC0 kind of the circuitry for all the chunks, and then with their outputs, I mean, I would be doing something else to observe something which is uh, beyond the capability of a single AC circuitry. at the constant depth, and therefore I require, I mean, more number of the levels. So is this possible? Then only we would be requiring, say, to move up in the hierarchy. If we have something which we cannot achieve through
Yeah, yeah.
constant,
Yeah,
so
that is.
then there will be a case. Yeah.
Okay. Yeah, I think, yeah, that I mean that's along the correct line. So I we want to show that there's something that, I mean, that cannot be computed by a combination of ACK minus one, but um, yeah, I mean, even if we use any choice of combinations, we can't get to ACK.
Yes,
But
yes.
yeah, but there's a, yeah. Mm, I mean, there's a maybe a neater way of showing it, which I can't think of right now. Okay, I'll think about it if there's something.
Yes, 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 yeah,
Okay, thank
thanks.
you. Okay.
Probably this is something similar to what we when we include more number of the hidden layers in a neural network, because we think that the single hidden layer probably cannot identify those patterns which multiple hidden layers can. That sort of thing. Yeah. Thanks. Yeah.
Okay. One thing is that I mean, ideally I would not like to argue this way, but one thing is that we know that AC0 is in NC1 and AC1 is in NC2, and yeah,
Why so? Why so?
because you can. Okay, so how does this proof go? Okay, so this is a general theorem that AC. Um, okay, ACK minus 1 is contained in NCK. So the idea is something like this, that for every unbounded fan-in gate, we're actually going to break it into a circuitry of bounded fan-in. So this is, we'll see a similar exercise here, and we will argue that it will not blow up um, uh, the height each time. It will not blow it up more than a factor of log n. So okay, so I mean, this is something we will do at every gate here. So let's say this is my AC0 circuit with unbounded fan in. Each of this gate is going to be replaced with a slightly larger circuit but with a bounded fan in, and similarly all of them. Okay, and eventually we will argue that each time the blow up is not happening by large factor. So at the end, um, if this were a depth D circuit, then the new circuit with bounded fan in that we get is D times log n at most. Uh,
Actually,
that's the
this,
new.
this, this, this argument is not clear actually. I could not, probably I missed something in between and I could not understand this thing. We are trying to show that ACK minus 1 is a subset of NCK. So how to show that? You started with something which I could not understand.
Okay, okay. So, okay, so we'll do our maybe first question, and I mean, that will clear up some, yeah, some
Yeah.
idea, and we'll come back here. Okay.
Sure.
So, okay. So,
Yeah, this is fan-in of a circuit is the number of the inputs to each gate in the circuit, and show that any Boolean circuitry having the fan-ins greater than 2 and the depth D can be converted into 1 with fan-in 2 and the depth at most D. Okay, so if I have been given more number of the inputs, like say if I have been given and maximum I am allowed to, so I am allowed to take two inputs at a time. And in the original circuitry, the depth is D. So then, if I can take maximum two inputs at a time, so then, I mean, how to realize a single gate and which has got n number of, but then these n number of the inputs are spread there over the height of the over the depth of D. So at a particular level maximum how many number of the nodes would be there? So at a particular depth there would be say maximum 2 raised to the power d number of the nodes would be there. So if there are maximum 2 raised to the power d number of the nodes, and now the probably the question is that how can I simulate these 2 raised to the power d number of the nodes while using maximum 2 number of the inputs at a time. So can this be done and without increasing height much? Because we have to convert it into the height of the order of d only. So if that is the case, if I've been
Um,
giving 4 inputs, so how to simulate this thing by using say by taking 2 at a time.
okay, just
So
a minute. Okay, so I just one thing. So you are starting with a fan in K circuit. Okay, so let's say that the top gate has a K fan in, and then the other gates that are feeding into it also have K fan in each. So at depth D, the most the I mean maximum number of gates you can imagine you have at this level would be D to the K. Oh, sorry, K to the D. uh, I mean at depth D.
yes. I
Okay.
understood. Yeah, because this is not the binary case.
Yeah,
Yes,
yeah.
yes.
Okay.
And then I have to break this. I have to simulate this k raised to the power d in terms of the 2 raised to the power d kind of a thing.
Hmm. Hmm.
And how can this be done? So if at a point say, so can I take say if the value of k is equal to 4. So can I break this 4 inputs? I mean, how
Hmm.
to two at a time.
Hmm.
So probably that can be done
Hmm.
that if I take 2 inputs at a time, because if you give me 4 inputs, I can always uh, uh, include the brackets in such a way so that everything can be broken down as a combination of two. That can be done. That can be
Right.
done.
Right.
Yeah.
So yeah. So we have and k uh, or k and negation gates that are there with us, and we want to convert it to and with two or of two variables and negation. So this is out of the picture because negation is anyway a unary um, operation. So we need to simulate and k by using or sorry simulate and k using and two gates, and or k using or two gates. That is what we want to do. So the argument for these are very symmetric arguments, so we will do this for sorry. Okay, so okay, so let's look at this top and k gate, and it takes k many wires. Okay, or let's say four for now. Okay, and I want to simulate it using ANTU. So like you said, what I can do is I can okay, let's do four. I can think of the and think of it as a tree. So just split it into a binary tree. So in general, if it is and k, then what we will do is we will split it into uh, and assuming that it is a power of 2. For now, let's assume that uh, k is some 2 to the l, then the depth of this will be l.
Uh, so k is equal to yes, that's correct.
Okay, and now we want to argue that they are computing the same function. So we know that I mean this function is going to be 1 if and only if both of them are 1. That will happen only if all the inputs here are 1.
Right.
And these wires, I'll call it w1, w2, w3, w4, sorry. Okay, these are nothing but the wires at the last level here. So this is w1, w2, w3, w4. So these are something extra wires that we added in the tree, but these these are the these correspond to the wires that are going at the last level.
Yes, yes.
Okay, so this is something we did for the root gate. Now what we will do is, let's say that G1, G2, G3, G4, these are the gates that were that take the wires from that the wire W and W4 are attached to. Okay, so what's really happening is that these gates G1, G2, G3, G4, and so on are sort of here, and it could happen that, let's say, G1 is an OR gate and it is computing an OR of k variables. Then what we will do is we will replicate that tree again with uh, with a depth of L, and we will continue. So it's an iterative process.
Yes, but then we are increasing every time we are increasing the height by a factor of what? By a factor of two.
By
And
a
then
factor
we
of L, yeah, yeah.
so if it is by a factor of two, then we won't be able to maintain the height of the converted tree of the order of t. We would be requiring say exponentially large height of the depth of the tree.
Right. So yeah. So what you are saying is that each time we are increasing the height by a factor of L. So altogether, finally, what will be the height of this? It will be, um, if initially it were D, let's say.
Yes. So if it initially it was d, so then it becomes what? It becomes what? Say it becomes uh, 1 2. So it becomes not 2D but then D plus 2, D plus 1, D plus 1.
But we're doing this every time, no? So for, um, I mean, um, let's say this were a depth 3 circuit initially. Okay, I mean unbounded thing. For the first gate, we increased by a factor of L.
Yes.
Okay, for the second time also we increased by a factor of L, for each of these.
And we wrote L as what? K is equal to 2 raised to the power L.
L.
So what is uh,
Huh.
L
L here
is
is log K. L here is at most log K. So we are thinking of the nearest power of 2.
yes.
Okay. Okay. So, hmm. So for this one, we increased by a factor of L. So, um, it became, sorry. So this is L. Then at the second level also we did the same blow up. So again this increased by a factor of L. So each time we are at every level of the depth we are adding a factor of L. So this is D times, right?
Yes, but then I forgot that why did we write this expression say K is equal to 2 raised to the power L and from where this L came into the picture.
Oh,
Uh,
okay, okay. So what we were saying is that, let's say K is a power of 2.
yes.
Hmm. Then this is a complete binary tree.
Yes.
Okay, but if K is not a power of 2, even then the blow up that is going to happen is the same as what it will be for nearest power of 2. There may be some some gates here that are, it may not be a complete tree, right? So for example, if K were 5, okay, so what will we do? Okay, sorry, I'll use some other page. Hmm. So if K were 5, even then the blow up that will happen is, in the height, is the same as what it would have happened for 8. So it's just that we did not use this part.
Yes.
Sorry, these are the wires, sorry. Hmm. So, um, yeah. So that means the height that we ended up uh, increasing was by a factor of log 8 in this case.
Yes,
Okay. And
yes, but even this is not clear. So k is equal to 5 would mean that we have been given uh, say
5
five
layers.
five inputs,
Hmm.
right? And then we are breaking it in the binary tree form. So if I break it, then this k becomes 8. How? I mean, one,
No, no, no.
two, three.
So k doesn't become 8. I'm saying that even if k were 8, what would have happened is that the
The same complete
it would
binary
have
tree.
been the
Yes.
same height.
Oh yes, yes. Right. It's okay.
So the height increase that happened is log k log 8 to the 2. We won't write log 5 to the 2 because that is not correct.
Right. Yes.
So that's why we are using this nearest power of 2.
Yes.
Okay. So okay, and this part is fine, no, that every time we are adding the height by l,
Yes.
so at the end it will become l times d.
Yes.
Hmm. And if k were a constant, um, it could be a very large constant, say it is 100, but it is still given as a constant that okay, all the gates have a fan of 100, then this l is also going to be a constant.
Yes.
Okay, and
Yes.
then this is nothing but order t.
Oh
So
yes, of the order of t. Right. Yes, and assuming that this k is a constant,
hmm.
it could be a pretty large number, but then this is a constant, right? Usually, what happens with the finance? I mean, can we represent finance as something like say n square or n cube, or will this always be a finite quantity?
Hmm. So this is always bounded by n, at most n.
Oh, so if that is the case, then if L is of the order of n, then L will no longer be a constant. So then that will become of the order of n square, or say nd, and
uh,
then this won't
log
be
n,
valid.
because k is n, so l is log n.
Yes. So if L is log n, and if L is not constant, so then it will become say of the order of d log n kind of.
D log n, exactly.
So
So that is exactly the argument for this that we did. So think of the and or unbounded sorry, what am I? Or an and an and negation. So we are simulating that with and to or to and negation, like the same idea that we did. So this is what I was drawing earlier, that this is the unbounded fan-in circuit, and we're going to replace each gate with a slightly with a tree which increases the height by some factor that we yeah, that we'll see. Okay, so that is what is going to happen. So the height of this new tree is going to be l times t, where d is the original height, but d for us is k minus log to the k minus 1. Okay, because we are at AC k minus 1, and this L that we saw, because um, sorry,
instead of L, this should have been say uh, this should have been some other quantity. Say it's the original input. So if you so you can write it as some quantity say n here.
hmm,
So if you write n here, so basically what we want to show here is that whatever, if I allow every gate having many inputs, then whatever it can achieve at the level of k minus 1 can be achieved with, if I restrict the number of the inputs to 2 and I increase the depth or height, I mean by an amount of say
factor of
1.
log n.
So the k, I mean this is k here. So in this theorem it is AC k minus 1 and then NC k. So But then this result seems so very unrealistic, isn't it? Say if I allow say 10 number of the inputs for a gate, and I can achieve things at the depth of say k minus one. Not k minus one, yeah, then but then log raised to the power k minus one probably. And then if I restrict the number of the inputs to every gate is equal to 2, and then I can achieve the same thing in the depth of the order of log raised to the power k. This is justifiable because I am increasing everything by an amount of the log, and which you showed just now. Yeah, makes sense here. Thanks. Yeah, clear.
So this is log n for us, like you said. So altogether, the new depth is log kn, and this is our NCK by definition.
Yes, yes.
Okay. So, yeah, to answer your previous question, so one argument would be that, although it is not very elegant, one argument would be that we know that AC0 is contained in NC1 and AC1 is contained in NC2, and with with the bounded fanning, it is, I mean, it's sort of more intuitive why this should be more powerful than this. So, so a separation here sort of tells us why there should be a separation here, that this may be more powerful than this one, but there should be a direct argument for that. So I'll think about, yeah.
Yes, yes. But then in the course of the data structure, we used to study that every general tree can be converted into the binary tree. Are we not using
Every
every general tree?
general,
Every general tree can be converted into the binary tree.
huh.
So are we not using that kind
Yeah,
of
yeah,
argument here?
yeah, that is, yeah, what we actually um, ended up doing, yeah.
Oh, yes, yes, yeah, fine.
Okay.
And this or thing would be simpler compared to and probably because in that case I just need to look into one of the value because we have to show this equivalence for the and as well as for the or.
So actually, it is exactly the same, that you will have to make a tree out of it, because you want to be correct for all the possibilities, right? Even if the function was 0 earlier, you want to be 0 now. Um,
What does it mean? Say, so say if I'm computing for, it is just sufficient to see that one of them is uh, but then in that case, what if I mean one input is not one? Then I have to look into both the inputs, and then
exactly.
the things become similar. And that's right,
Yeah, yeah.
right. Yes.
Okay.
So the fan out of okay, fan out would mean that uh,
The number of outgoing wires from a gate.
okay. So can we have more than one outgoing wires from the gate?
Yes,
Okay,
yes, perfectly
okay,
possible. Yeah.
okay.
So this could be
So
feeding into some other gate. This could be feeding into some other gate, and could be.
okay, okay, yes. So the fan out of a circuit is the number of the inputs. Fan out of a circuit is the number of the inputs to each gate in that circuit. What does it mean? The fan out of a circuit is the number of the inputs to each gate in that circuit.
Okay, sorry, did I write it wrongly? Sorry, it should be the number of outputs that are. Sorry, I think I just copied the previous question. Yeah, I think I copied the previous question. So this is um, the number of outgoing wires.
Yes, yes. Yes, and so, but then how to know the fan out of the entire circuit? Because we can think of the fan out of an individual gate, but what
Sorry,
would be the
yeah,
fan
yeah.
out of?
Sorry,
Oh,
sorry,
I
sorry.
see,
I'm sorry.
I see.
Yeah.
Yeah, right. So the fan out of a gate is the number of the outgoing wires, and so that any Boolean circuitry and with fan out greater than two, any Boolean circuit, so and def t. So there is a little confusion here. So that any Boolean circuit with a fan out. So what's the meaning of the fan out of the entire circuit? Fan
Uh,
out of the entire
that
circuit.
every gate has a fan out bounded by K.
Oh yes, yes. So then and depth D can be converted into a fan out two, and the O. Okay. So now in this case we have to. Okay. So instead of the uh, so now we have to think that so because something which is output for a gate will become input for the other gate. So if that is the case, then the previous argument will still hold true for most of the gates except few ones. And what are those? So those gates uh, would be uh, would be probably at the second last level, because in the uh, last level we are giving input, but then last level there is no input as such. Last level is for the inputs only, and then in the first level we are giving input. Yes. So in the second last level, I mean this will hold true for the depth d minus one. For the depth d minus one, this is not an issue. The depth would remain as of the order of d only, and we can convert everything, say k, into an order of 2. Just now we showed this thing. Now the only thing remaining is that the last level wherein uh, we are getting inputs, but uh, that will not increase the height depth much. So is this not a valid argument that the outgoing edges, because the outgoing edges for one of the gate will become the incoming edges for another gate. And since for the incoming edges we just show that this can be done in the depth of the order of d only, so therefore this argument holds true for the outgoing edges as well.
Okay. So, okay. So, um, let's look at this particular circuit. Okay, I'll just draw one circuit. Um, mm, okay, I don't think this is even needed, but okay. So, um, in this case, if we look at the fan in of each gate, that is bounded by 2. So here you have two inputs, 2, and here just 1. Okay, just to make it uniform, let's say it is coming from somewhere. Okay. So here fan in for each gate is bounded by 2, but is it true that fan out is also bounded by 2 for each gate?
So fan out is not uh, uh, okay. So right. No, no, it is not true that the fan out is not bounded by 2.
Because this one, for example, is violating that. So it could be that there are a lot of wires that are going out through one gate, but maybe it is not all going to the same gate. So maybe altogether each gate is just taking 2 of them, but the extra wires that are going could be going anywhere else. So because of that, this does not guarantee that the fan out is bounded by 2. So the earlier argument will not work in this case.
Yes, yes, yes. So if that is the case, then so now I need to show that I can restrict the number of the outgoing wires by 2. And even if I have many wires, so like say in this red's node, 3 wires, 3 are the outgoing wires. And if I want to restrict it to the 2, then what I need to do? So probably in that case, what will I do that if I want to restrict it by 2? So I can, but then since I am already interested in the depth, so is it possible that I create a duplicate of it or dummy kind of it,
Exactly. Yeah,
and
yeah,
then I
yeah.
go for it?
Yeah, that's the correct idea. Okay, so I'll just write down all the steps that we did so far. So we observed that this is um, not true, that fan in at most 2 does not imply that fan out is at most 2. So the previous argument does not apply. Okay, so what you're saying is that what we'll do is, let's say this gate is going into three other gates. I'm going to duplicate it. So let's say this is a dummy vertex node which also computes the same function. So um, I'll erase this wire and pass the output of this gate through the other dummy. So if the fan out of this gate were k, then how many dummy nodes do we need?
Okay, so similar to the previous argument, then we would be requiring, like in this case, we double the things, and so we would be keep on dividing it into two. So log of not log of k. So I'm just doubling it. So
K
k,
by
and I would be requiring say to restrict it to the number of the two, and so except two for the remaining k minus two, I would be creating for everyone. I would be creating a dummy. So then I would be requiring of the order of k number of the nodes here.
exactly. So earlier, if this gate were feeding out into with k wires, then what I'll do is I'll make k by 2 many copies of um, duplicates, or okay, and 2 wires are going out through each of them. So altogether we have a fan out of k still. Okay, so this is, yeah, you're right, so this is order k. Okay, so so the point is that at the top level it seems okay. So let's say this were my output gate, and okay, output gate anyway has a fan out of 1, so it is out of the question. Let's say hmm, okay, maybe at level 3 or something. So mm, yeah, okay, so not a very nice example, but okay, let's work with this. So um, okay, the point is that if this gate here was feeding into 3 other gates, then I'll have to duplicate this. Okay, that's what we said just now. But in order to duplicate this, what I'll have to do is that the entire circuit that was there below it has to be duplicated again. Okay, so that would mean that if this gate G1, G2, and okay, whatever gates were feeding here, I'm kind of going to have to duplicate them, because I can't use the output of this, which was feeding here, uh, again here, because maybe it had this quota of 2 wires, so maybe it is using that already, so it is getting exhausted within this circuit. So I can't hope that okay, I'll just extend this computation that was done at intermediate level and feed it directly.
Yes, and that would be problematic. So, what can be done that conveyor? There should be some mechanism to bring the intermediate calculation out of the node. And so whatever calculation has been done till this node, we should be able to bring it out. And for that thing, what is required is so this is given three, like here three, fan out is three, and we have copied this thing. The entire lower, it is not advised to copy the entire lower circuitry.
Okay.
So,
But
yeah.
okay. But in this case, would it even matter? Because let's say I do that, the most naive thing. Okay, I'll copy it as many times. Okay, I mean, it will be a huge blow up in the size. Okay, I'll copy it as many times as I want. Same thing happens at every level. So we can imagine that this circuit is, I mean, becoming a very large circuit in terms of size. But notice that if I were able to compute this particular function or output at level k, some level, okay, I'll call it level L, then I'll also, I mean, I'm not increasing the depth at any point, right? Because if I were able to compute this at level L, I will also be able to compute it again at the same level, right? So I'm just increasing the size but not the depth.
Uh, yes, yes,
So even though this huge increase is happening, it's only happening, like it's becoming fat in that sense. So that there will be a lot of extra dummy gates in that, in every level, but it will not increase the depth even by one.
yes, yes.
Okay, so this is so that proves that, so in fact we are not doing at most order d, we are doing just d. Okay, but you're right. So if I want to, if I'm worried about the size also, then the amount of blow up that is happening here is huge. So if it were a poly size circuit, it is no longer a polynomial size circuit if we blindly duplicate at every point. So I think we'll not do this exercise this time, but when we talk about formulas in the course, so what are formulas? Um, so formulas are special circuits where fan in of each gate, okay, sorry, fan out is bounded, okay. Okay, sorry, I'm sorry, I should check it, okay. Or are you aware of this?
No, no, no. No.
Okay.
I don't. Even this term was there, not there in the lecture video, I guess.
Which term?
This formula term.
Okay, okay. I think it will come up in later on in the upcoming weeks. Okay, it's fan out. Okay. So okay, okay. So fan out is bounded um, by one. So basically, if you look at the underlying tag, it will be a tree, because uh, it's only allowed to have one output wire.
Yes, yes, yes.
So these are very um, restrictive in that sense. So we can imagine that circuits could be more powerful. I mean, if you allow the same parameters. So between depth D formula and a depth D circuit, what is more powerful? I mean, assume everything else is same. So the gates are same, basis is same, fan in and so on is also same. But the only difference is that I'm allowing the the way the wires are placed. Here we are making it more restricted by saying that the fan out is at most one, and here you are allowing it to be arbitrary, and everything else, every other parameter is the same. So the question is, can there be functions that can be computed by um, depth D circuit but not depth D formula?
I guess both should be equivalent. I do not have any logic of it, but then like in the in the log functions, so it doesn't matter whether we have a base of 2 or the base of 4, unless I mean the value is greater than or equals to 2. The things are going to behave more or less in the similar way, because we have that log identity also, that we can always change the base in the constant effort, in the constant time. So I think that both should be equivalent. I don't know that how, I mean, this can be achieved, but yeah.
Okay. So, um, yeah. Okay. So we will look at questions like this in the upcoming week. So I'll not extend this more on this, but I just want to bring it up because we talked about the fan in fan out. Okay.
Okay.
And what else? Yeah. Another thing to connect is that the formulas that we talked about, right? The CNF, um, DNF, I mean, when we say 3 SAT and so on, we wrote it like this, x1 or x2 or x3 and so on, right? So if you look at it, visualize it as a circuit, it's basically a formula, because the fan out of each of the gates here was 1.
Yes,
So
yes, yes.
it was just a
Yeah, and every Boolean formula can be written in the form of the CNF. That is also correct.
right. So yeah, so these were the same formulas um, that we were using. It's just that we did not define it that way because that time, because we hadn't introduced circuits. Okay, and this circuits versus formulas is I mean, it's a very big field that is being explored. So the one reason is that we study formulas is that um, it has a nice structure, right? That it's very restricted in the sense that the number of outgoing wires for each gate is at most 1. So it might be easier to prove some bounds or do some analysis on this model than it is for circuit. So that's why that is one natural restriction that people study. And um, yeah, I think yeah, in the upcoming week, I think we will have detailed. We will see some random restrictions and all those arguments. So I think more stuff will come up on this. So okay, good. Um, yeah, okay.
So a Boolean function is called monotone, and if x is less than y, then the f of x should be less than or f of y. Wherein x and y would mean that x is okay, but then these x and y's are all zeros and ones. So, but then what does it mean that x is less than or equals to
Mm-hmm.
y?
Good.
One thing,
So,
and yeah.
so what we say is that, let's say x is a boolean uh, n bit string, and y is also a boolean n bit string. Okay, so this is x and this is y. So we say that x is less than equal to y if, or in this case y is less than equal to x if I look at every place. This is x3, x4 and so on. So at every place it should happen that this value is greater than equal to, okay, I think I'll make it easier by swapping. Okay, so here the first value is less than equal to the second value. Here also the first value is less than equal to second value. Here also, I mean, that happens for each column. Okay, that is
Yes,
for
yes,
all
yes.
xi less than for all xi is less than equal to y. Then you say that uh, in this particular ordering, we'll say that x is less than equal to y. In any other case, for example, if there could be cases that are not comparable, right? So for example, 0101 is not comparable from uh, mm, yeah, it doesn't matter what I write. This is not comparable, or to make it simple, 01 is not comparable with 10 because there is one column where the first, let's say x is greater than y, but there is also one column where the other way around happens.
Right, right. Yes,
Right.
I understood. Yeah. There should not be any inconsistency. Sometimes we say that, yeah, this column is greater and the other one is small, right? And a Boolean circuit is said to be monotone if it only uses and the OR gates, no negations. Oh, I see. Uh, no negation. So will this be the complete one without negation? No, it
That
won't.
is, yeah, that's a very nice question. So there are functions that cannot be computed by monotone circuits. For example, just the negation gate itself, right? You think of this function, um, and output is 01. Think of it as a function on one variable only for now. So and NOR gates both cannot compute this.
Yes, yes, yes. Right. So now the problem is to prove that if f is monotone, if f is monotone, would mean, okay, this inequality holds true, implies that f can be computed by a monotone circuit. Okay, so basically I need to show that if a function is showing this much of the consistency, that every column is either greater or equal, then I mean in the comparison, like say if I want to show that x is less than or equals to y, then every column of x would be smaller than or equals to the
Uh,
every column of y.
okay, so this description is just to define the left hand side. When do we say that x is less than equal to y? But the function is monotone if whenever this happens, for every pair of x and y where this happens, if let's say the function was computing a value of 1 year, it cannot be that it suddenly becomes a 0. That is what it is saying. So if they are holding this ordering, then yeah, this cannot happen, that the value of f of x is less than the value of sorry, greater than, that's what I wrote, no? 1 is greater than 0. This cannot happen. So if this is 1, it will have to remain a 1. If it were a 0, it can happen, it could be that it became a 1 now, but it can't be that this was a 1 but this became a 0.
Oh yes. So like in this case, in the second column, say for x2, so since x is smaller than y, so that would mean if I apply f of x here, so this, I mean towards the x side, this value can become 0, but towards the y side, f of y cannot be a 0 because the value of x is 1. So I have to take care of this thing, that if x is smaller than, so if x is a 0, then the f of x has to remain a 0 if x is less than or equals to y, and if y is a 1, and then f of y could be a 0 or could be a 1 as well. Okay, and this can be this can be so by a monotone circuit, and this entire thing can be done in by just by using and ors and without using any not. That is
So
a thing.
that is one direction of this. You also have to show the other direction, that if it is a monotone circuit, then the function that it's computing is a monotone function.
Yes, yes, yes.
So
So yeah.
I think the backward direction would be easier, maybe. Okay, but yeah, go on. Yeah.
So yeah. So if I have to use only and ors, so like say if it is so if I take end of uh, so 0 and 0, its end is a 0 and the 0 or 0 would also be a 0. But then if it is 1 and 1, so this end should be maintained, that if it is 1 and 1, so n would be a 1. And if it is or But what if it is in 0 and 1? So in 0 and 1, the end would result into a 1 and it is following my strategy or not. So what if I take OR? So OR is fine. Uh, but if it is reverse kind, say 1 and 0. So for 1 and 0, the end will return 0. And so, yeah, so difficult to how to represent this thing. So if I take end of both, so if x is small or if x is 0, then y could be a 1 in the case of this x is less than y. If x is 0, y could be a 1. So,
Okay.
yeah,
Yeah.
difficult to, I guess.
Yeah. So, but you're almost there. So, let's say that this is the circuit, the monotone circuit that we have. So, it only has AND and NOT gates. Okay. Now, we want to show that um, that whenever x is less than equal to y, this is our input x1 to xn, and I'll call it x prime just for. Hmm. Okay, so whenever this happens, we want to show that f of x is less than equal to f of x prime. Okay, so let's say that x is some arbitrary input that we are talking about. So x is x1 to xn, and when does x prime become greater than equal to x? If there is some column where uh, this was okay. So okay, one thing here is that uh, whenever this happens, there has to be one column where x was 0, I mean xi was 0 and x prime became 1. Otherwise it will be the same, it will be the same input as x. So
Yes.
yeah, so there has to be a column xi where, or I where xi was 0 and xi prime became 1. Otherwise, unless x is same as x prime, which I mean, which is not interesting for the matter, right? So there's nothing to argue otherwise. So, hmm, okay. So this is what happened, and there was some 0 here, and it became a 1. It could happen multiple times, but let's say for now that we are talking about this particular place I where this happens. So let's say our xi was here, and it was a 0 earlier. So and now it became a 1. Okay, so can it be that okay, I'll zoom into this thing. Okay, so let's say it is feeding into an OR gate for now. um, okay, so if this became from okay, sorry. If xi were 0 earlier and now it became a 1, xi prime is now 1, then whatever was being computed at this particular gate, it cannot be that if it were a 1 it will suddenly become 0. If anything, it can only increase, right? Because it's an OR gate. So earlier, let's say this is 0 and this is 0, maybe it was computing a 0, but because this became a 1, the output here can only increase for this particular gate, right?
Yes. Yes.
Okay,
Right.
and the same argument applies everywhere. So let's say this guy is feeding into some AND gate. Okay, we'll make the same argument for AND gate also. If xi were feeding into an AND gate, and this was, let's say, 1, but xi was 0, so this was computing a 0. But if xi is now 1, then it is computing a 1. Or if this was 0, then it is still computing 0, so there is no change even after flipping xi.
Right.
Right. So what this means is that whether xi is feeding into an OR gate or an AND gate, it will only increase its output value for that particular gate. And same thing iteratively goes for all. So wherever this is feeding, it's an AND gate or an OR gate. By changing its value from 0 to 1, you are only pushing that either 0 to 1, or you are at the same value as earlier.
Uh,
Huh.
yes.
So this thing will conductively follow all the way to the root. So eventually, either we are computing the same value or we went from 0 to 1.
So, yeah, so I was thinking that since you compared, since x is equal to say x1 and say till xn, and say y is equal to y1 and say till yn, assume that the length of both the strings are same. So then can't we use, because I mean, can't we use dynamic programming kind of a thing here
Hmm.
that,
Hmm.
yeah, x1 to xn minus 1 and then
Hmm.
y1 to yn minus 1, and then we put this argument only for the xn and then yn,
Hmm.
and then we can complete the proof here.
Yes, good. Yeah. So you can think of it that way. So think of um, x1 to xn minus 1 being computed at this point, and then there is this xn, and there's something that we are finally computing using this value and xn. So now assume that the statement is true for this, and then you only need to argue at this point.
Yes.
Good. So yeah, you might need this kind of an idea for the other direction. That is, if f is monotone, then there's a monotone circuit corresponding to it.
Yes. So if f is monotone, that would mean that yes, uh, it is only using the and then the argument, and so if f can be computed, if f is monotone, oh yes, f is monotone if this inequality holds true, right? So if this inequality is holding true, and then till xn minus one, this entire thing is being followed. So then for the remaining thing, yes, we can achieve it by using the AND and the OR gates only, because if what if so? I mean, can we have some counter example here? Like say if f is not monotone, then how to show that this cannot be computed by a monotone solution?
If okay, so what is the direction?
So if
If
f
f
is
is
fully,
not computable by a monotone circuit, then f is not monotone.
or even in this direction, say if f is not monotone,
Hmm.
it means that if x is less than or equals to y, and
Hmm.
we found that either f is inconsistent
Hmm.
or fx is greater than or equals to
Hmm.
y, then how to show that this cannot be achieved by the
Hmm. But that is same as what we proved earlier. So if we say that f is not monotone, implies that it cannot be computed by um, monotone circuit, then this is same as, I mean, the converse of this would be that, so p implies q is same as not q implies not p. So this is same as saying that if f has monotone circuit, then f is monotone function. This is what we argued here anyway. So if there is a monotone circuit, then it is computing a monotone function. So either we will have to show that um, f is monotone function implies there is a monotone circuit for f, or if you want to go for with the negation, then the correct thing would be that there does not exist a monotone circuit for f, implies f is not monotone. But this might be harder because to say that there is no monotone circuit means that you are arguing, means that you are arguing with respect to all possible circuits that there can be. So that could kind of make things um, harder.
Yes, yes. And now since we have proved the other direction, and in the question what is remaining, the forward direction is remaining to be proved.
Yes, this. So this is done. This is what we want to show.
So if f is a monotone function, then so then I mean, where is the difficulty? Because if f is a monotone function, then if x is less than or equals to y, then the f of x is less than or equals to f of y. It means that if I mean 0 is not going to become 1 at any cost. And however, if it is a 1, it may become a 0.
So this
Yeah.
is with respect to the function, but we want to show that there exists a circuit which only contains and or gate and computes f. So we, mm, um, I mean, we'll have to show that there is a circuit, right? Um, that there must be a circuit with only and or gates.
Yes. So, uh, but how to
Hmm.
is this argument alone is not sufficient, or we need to do something else? I'm unable to think.
Uh,
Yeah.
so using this argument, we nowhere talked about what are the gates that are being used to compute it. It could be
Yes.
that I'm using negation gate there. So,
Yes. 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 Right. So if it is a zero, it can be a one. It cannot be a one.
hmm.
So if it is a zero, it cannot be a one. Would mean I cannot use OR gate, and I can only use AND gate. If it is a zero, uh, yeah, not able to think actually.
So this idea that you mentioned is the starting point of so this idea of solving it for a smaller sub problem and then building the solution for the bigger problem is exactly what we will
Okay.
use. So think of how do we define the sub problem. So so f is a function on n variables. Okay, so think of it as computing some sub function g on x1 to xn minus 1. Okay, and we will assume that the statement is true for g. That means the g is a monotone function. So um, so there is a monotone circuit for it. So this can be computed just by using and or negation gates. This is something we will assume. Okay.
Yes, and now only two possibilities are left for the xn, and then so the one possibility is that we have a value 0 above and then 1 below. Uh, can you write those values as 0 x, the value of x then? Yeah. So we have uh, 0, yes, uh, and the other possibility could be that so 0 0 case, it could be last one. The 0 0 case, 0 0, I mean that we are comparing the xn with the yn. Probably you have not written anywhere in this table the values of the yn. And I mean to say that I would be comparing, say, the value of xn is a 0 and the value of yn is also a 0, one possibility. Other could be, say, 0 1 1 0 and then 1 1. So out of these four possibilities, which are irrelevant, so 1 1 is quite irrelevant and 0 0 is also quite irrelevant. Now we are left with only two possibilities. 0 xn is 0 and the yn is a 1. or xn is a 1 and the yn is a 0. So if it is a case of 0 and 1, then again I am not bothered. So what is left with that I am left? So 0 and 1 and 0. I have to handle these two conditions by using the and the or gates. Uh, and so if it is 0 and 1, then I can use which thing? I can use 0 and 1. So I can use OR gate and I will get a 1. The things are preserved. And if it is a 1 and a 0, then this is not a monotone function. Then I should use AND. So this thing should be done somehow.
But how do we capture this if if else condition using the gates only?
Okay, so the thing is like this that since till n minus one the things are perfectly fine somehow, and
So I'll call this function G. So there is some circuit corresponding to it that I already have, and this could be a different function, right? This need not be the same G. This could be some H. It is still monotone, but okay. So how do we? Okay, okay. So we'll look at the output values here, and it's some boolean values which respect the monotone property, that if x is less than equal to y here, then you can't go from 1 to 0. It respects that, but these could be some entirely different. These could be some entirely different. So for example, for all zeros it could be a 1 here, then it will have to be a 1 everywhere. um, so these values are independent of these values.
actually this is not clear. When you write this output as a new column, so what does it mean? I mean, whose output is
This
this?
is the this is the output of the function f. So this is
Oh,
the
I see.
truth table of f.
Output of the function f, output of the function f, but then we don't get a single output of the function f. Rather, f is a monotone function. Nothing is specified about this function f. The only thing is that it preserves that inequality and nothing else.
Hmm.
So how are we getting the value of the output as a single
As
absolute value?
I'm just writing random values, just saying this is some 0 1 string which respects the fact that it is a monotone function.
But yeah, so that is actually this is difficult to understand that even if this function f is a monotone function,
Hmm.
so I mean, are we getting some actual value? Say if whenever we are comparing say x1 with y1,
Hmm.
so then are we getting some absolute value of the function f that okay if we are comparing 0 and 1, then this value would be a 1 because the inequality is being preserved here, or in that sense. So I mean, how are we getting this output which you wrote in the blue, this
Okay,
0
okay,
1
okay.
and 1 0?
So I'm not computing it, but what we are given as input is a function, right? From n bits to 1 bit.
Oh, I see. Yes, yes. Now I understood. Yeah.
Okay. So we will not need the exact values, but we are just writing it in the form of a truth table.
Yes.
Right. So because so we can think of f as two different functions. So okay, this thing also you agree, right? These values need not be the same as these values exactly.
Yes.
Hmm. So because 0 is freezed here, this function only depends on only depends on the x1 to xn minus 1 variables, this particular function.
Yes.
Hmm. Similarly, because xn is freezed to 1 here, the other half of the truth table only depends on x1 to xn minus 1.
Right.
Hmm. So this is this is also a monotone function. G and h both are monotone functions. So
Yes.
there is, by our hypothesis, so we will apply our induction on the number of input variables n. So base case, what would be the base case? Let's do that quickly. So let's say n is equal to 2, even 1 is okay, so let's do 1.
Yes, so if n is equal to 1, um,
Then what are the functions that are possible on n variables, that one variable, that are monotone?
yes, so it is to this is 0 and then 1 and then 0 0. That's it.
0 0 or also 1 1.
Yes,
Okay, so in this case, what is the circuit corresponding to it? Just output x1. I mean,
right.
and okay, this is like, um, I mean, kind of, yeah, trivial. So take the x1, take its AND with 0, um, and output that. And in this case, take an OR gate, add this 1 as its input and output that.
Yes.
So in all the three cases, mm, we have a monotone circuit corresponding to it. So
So yeah, if the value of x1 is 0, then you are getting the values as, I mean, I focus only on the first row. So if the value of x1 is 0, then I can have a 0. I can keep it as 0 or I can make it a 1. Yes. But if the value of x1 is a 1, I can keep it as a 1. But then how can I make it a 0? So this is not, uh, probably the third column is not correct. Third, and previous to this one.
this one.
Yeah.
Okay. So yeah. So what this says is that if x is less than equal to y, then f of x is less than equal to f of y. So this is less than equal to, right? So I mean, if this is 0, this is also allowed to be 0. That will still respect the inequality.
So when you write, say, x1, I mean, what's the meaning of the notations you are using? Like, say, the first column, you wrote x1 and the possible values 0 and 1. So
This is
what is
the
0?
function 1 that is possible. This is the truth table of the second function, the third function that is possible. Okay, so I think this is a little okay. So what we mean is that this is one possibility. That on one if the number of input variables is 1, then this is one possible function f1 that which is monotone.
So where is y1 here? I mean, with whom are we comparing?
So we will compare with the input variable, right? So in this case, this is x1.
Yes.
So, okay, I think I shouldn't have. Yeah, it's fine. So, whenever. So, this is our x1 and this is our y1 sort of. So,
Oh,
earlier what we did was if this is 0, 0, 0 and this is 0, 0, 0, 1, this was our x, this was our y. In this case, this is our x and this is our y.
yes, yes. So now that we have 0 1, so if we consider only this possibility 0 and 1, uh, so I mean, it's okay. Then we need not to even define the functions here. This is already in place. I mean, because x1
But
is already smaller than y1.
but it could be any function. So we want to show that this statement is true for any function f. Right. Uh, any f that is monotone must have a monotone circuit corresponding to it. Therefore, in the base case also, we will have to argue over all functions over one variable that are monotone.
Yes, yes. So even if you say that this first 0 is the value of x1 and the second, this 1 is the value of the y1.
Hmm.
So now we make some transformation here. So what are the possible transformations here? That this x1 remains a 0
Hmm.
and y1 remains a 1. The second transformation f2 could be that x0 remains zero, has to remain zero, and the second one could become zero. And the third transformation could be that this first remains a, but then that is not a valid transformation. So in fact, only two valid monotone functions are possible. F1 and then F2.
Okay.
If we think F3, and in F3, if what could be the possibility that zero remains zero, or one? But this is
But
already F1. This is already F1. This is already
so
a F1.
but this is 1 1, no?
Oh, I
So
see.
0 1.
So zero becomes a one, and then one becomes a one. Yes, so three. I mean, three possibilities are there, and we cannot think of any other possibility because that would be the
That
violation
would
of
be.
this monotone thing. Now this is clear. So, in the first case, say F1 is state is trivial, and in the second case, how to get the second case? So you are if you take compare say 0 and 1, and then I mean, how to implement this F2 then?
Huh. So, in the circuit that we had, along with x1 to xn, we are allowed to have constant values. So, think of 0 as one of those constant values. Take an AND of x1 with 0 and output that.
For this, one is getting converted into zero.
I can't hear you, sorry. Hmm?
So if we, what about this x1 is a 1 and then f2 becomes a 0?
Hmm.
So I mean this is a kind of the negation. So does this mean that we are taking say we are taking what? Even if I take end of this one with anything, does this mean that we are taking end of this x1, this y1 with a value 0?
Yeah, so we have one input variable x1, we are taking an AND of it with 0, so that the function always outputs 0. That is what we want. No matter what x1 is, we just want it to output 0.
Right, right.
So actually this AND gate is kind of redundant. What you could do is just take this output wire of 0 and give it as an output. That is also fine.
Yes.
Hmm.
And for this F3, irrespective of if it's 0 or 1, I can always take it or with.
Or with a 1. Hmm. So this is and sorry, this is a constant. This is called a constant 0 function. This is a constant 1 function because on no matter what the input is, it is always outputting 1. Okay, so that settles our base case.
Right.
Okay, yeah. Now we will use our induction. So what is our hypothesis? So the induction hypothesis is that if f is a monotone function on n minus 1 variables, then uh, f has a monotone circuit. Okay, and in this case, the g and h that we had, these are monotone functions on n minus 1 variables. So we know that g, h are monotone functions with n minus 1 variables. So there is a monotone circuit corresponding to these. So let's say I mean, for the sake of drawing, I'm drawing it separately, but I mean, actually, those are like this, but I'm just drawing it separately. Okay. So, let's say this is the circuit corresponding to G, and this is the circuit corresponding to H, and we know that it only includes, sorry, it only has and OR gates, both of them. Now, the idea is that I want to use these two circuits to build a circuit for f. We have one more variable xn, and I'm only allowed to use and or gates as many times as you want, but um,
Yes, but in this entire diagram, why don't we talk about the y1 and we tell why?
Okay, so y1 is not a new input variable, right? So when we compared these two rows, um, do we not have figure? Okay, okay, I'll just use this. So when we compared these two rows and talked about their values, so what were the variables? The variables were still x1 to xn, right? x1, x2, and so on up to xn.
And what about this y?
Uh,
This y, the second string?
this y, right? So these are
Yes.
just two strings from the entire truth table. So we had this whole all zeros x1 to xn, um, 0 0 0 1 and all the way up to 1 1 1 1, and here you have the value of f of x. Okay, so this x is nothing but one row from here, and this y is some other row from here. Okay, so when we say x and y, we are actually just looking at two possible inputs that could be to the circuit.
Oh, I see. And what about the output of this f? Uh, like
Hmm.
say you wrote 0 and then 1 here. So
So we are talking about these values in the truth table, that if this row is less than equal to this row in terms the input, right? Then if f was computing a value of 1 here, it cannot become a 0 here. This is what we were
yes, now the problem is that understood. Yeah,
okay, good.
I
So this
understood.
y is kind of confusing. So that's why I was trying to use this x prime later, but
Yes,
yeah.
yes.
Hmm. Okay, good. So, okay. So now the problem that we have is that we have two monotone functions t and h that are computing these these values, right?
Yes.
And now we just want to, so I mean, just to say in plain English, what we want is whenever xn is 0, we want it to give the same output that g is computing, and whenever xn is 1, we want it to compute the same output that h is computing.
Okay.
Okay, so let's say that you are allowed to use negation. I mean, actually, we are not, but for now, okay, as a digression, let's say you are allowed to use a negation gate. Then, how will you compute this? Same thing that we said just now.
So I put depending upon the value of the xn. If xn is equal to 0, I go for a g. Otherwise, I go for if negation of xn, then I'll go for h.
Hmm.
Yeah.
So that means, um, okay. So how do we write this? This is an AND of xn and h. If negation is true, then we want g, and finally we are doing an OR of that, right? So what is happening here is that when xn is 1, this the value computed here will become 0, so this will become 0, but
Yes.
xn is 1, so whatever is computed here is same as what is being computed at h.
Yes.
So what is being output is nothing but h. So when x1 is 1, we are doing h. If xn is 0, then um, yeah, then what will happen is the value here is 0, so the value here is 0.
So yes. So if the value is 0 here, then h and 0. So this becomes a 0.
0, and
Right.
this becomes a 1.
Otherwise, 1. Yeah.
So
And then whatever is the output of G, so that
g
will get accumulated here. And G or 0, the value will become itchy. Right.
Right. So this is because I mean we are allowed to use a negation, so we separately took care of uh, the two cases using the negation gate. But here the point is that we are not allowed to use negation gate. So um, so how do we do that? It's actually a very small modification of what we did just now.
Yeah, so if xn
Is one. Okay.
is one,
Hmm.
yeah.
Then
So if
mm,
xn is one, then I need to somehow
hmm. Okay, sorry. I think easier case would be okay. Let's do xn is 0. Then what do we want to do?
so if xn is zero, then we want to select g3, and
Hmm.
no. Then if xn is zero, then
Hmm.
we want to select. Then it is already there that we are taking and with g.
Hmm.
What is problem?
Okay. Okay. So if xn is 0, then you want g to g to be outputted. That means you want to inhibit h. You want to make it 0.
Yes.
Okay.
So
So
then for that I can use and here.
for that we will use AND gate here, right?
Yes.
Okay. Now let's do one thing. Let's just blindly output an OR of this. So what will happen when xn is equal to 1? Sorry, 0. Um, this becomes a 0, and therefore what is being computed is same as g. So this one part is correct.
Yes.
Okay.
And what if xn is equal to a 1?
Hmm.
So if xn is equal to 1, then I want to output h, and I want to keep this g hidden. So for that thing, if xn is equal to 1, then I want to output uh, h. So for that thing, I need to make this, but then if I use or, so then won't be of much use. And I want to output h if xn is equal to 1. So how to hide this g first thing, and how can I hide this g? So
Okay. So okay, good. So one thing is when xn is equal to 1, what is it outputting currently? What is the current output as a function?
it is outputting in the, I mean, the value of h,
Mm,
the value
okay.
of the table you showed earlier.
So
Of the
here,
table. If
what
xn
is
if okay, say
yeah
here
what
if the xn is a 1, then it is output the value of h.
okay, so okay, let's do that. Okay, so if xn is 1, then you are right, here we are doing AND of 1 and h. So at this point we are computing h. Okay, but then we are doing an OR of g and h.
Yes.
Okay, so this circuit is outputting g or h, but we want h.
Yes.
So now this is where we'll use the fact, until now we didn't really use the fact that g was a monotone function, h was a monotone function in this circuit computation, right? So now we will use the fact that f is a monotone function, g, h are monotone functions, to say that g or h is nothing but h.
Okay. And how can we say that if G is a monotone, uh, then G is a monotone, then the function properties are preserved. I mean, G will not violate this thing. Till now, nothing has been violated from x1 to xn minus 1. Nothing has been violated from the second edge as well. And now we are getting this G or H. So G will also preserve monotonicity, and the H will also preserve for xn. How to say? No, not that
Yeah,
clear.
yeah, good. So we will look at the truth table now. So this is what we had. We had a G here, then we had all zeros here, and then we had H here, and then all ones here. Okay, so um, okay, so we want to show that G or H is same as G. So um, notice that whenever um, this x1 to xn values that G takes is the same as the x1 to xn values that H take, only that we drew it like this for simplicity. But the moment you fix the values of x1 to xn minus 1, we are also fixing the values for H, right? So if I'm looking at one particular row here, um, 0 1 1 0 1, something like this, okay, um, there is also the same corresponding, sorry, we also have the same corresponding row uh, in the second half, no? So this is 0 1 1 0 1 1. The only difference is that, I'm sorry, okay, these are all zeros. Hmm. The only difference between these two strings is that this is a 0 here and the xnth bit is 1 here, right?
Yes.
So um, I'll call this x for now, this particular whole thing. Um, these values of xn minus 1 appended with a 0, and this is our y or x prime, which is the same values but appended with a 1.
Yes.
So what do we know about the relation between x and x prime?
So we know that till n minus 1, so x is less than or equals to say x prime.
In fact, it is exactly the same. Uh, we are looking at the same.
Yes, yes, same,
Hmm.
same. So these are same, and moreover their transformation is also same.
Mm,
So it would mean that g of x.
okay, by same we mean that up to n minus 1 it is same. But then if we look at the nth bit, it is a 0 here, but it is a 1 here. That is the only difference. So it differs only in the nth bit.
Yes, yes.
Hmm. So we know that x is less than equal to x prime.
Right.
Hmm. So what that means is that f of x is less than equal to f of x prime.
Oh,
By because f is a monotone function. So by definition, whenever this happens, that
yes,
I mean
that's true. Yeah, true, true. But how to make a circuitry for this? That is the question. Yeah. So,
exactly. So we drew the circuit for this, right? And we are now arguing that the circuit is correct. So by correct we mean um, so when xn is 0, it should be computing g. When xn is 1, it should be computing h. This is what we want to argue. This part we did.
yeah.
Okay, and now our circuit is computing G or H,
Yes.
and we want to show that this is nothing but H. We are not changing the circuit now. We just want to argue that although it is computing G or H, but because it is a monotone function, it is same as H.
And how are we showing it here then?
Hmm. So um, okay. So how do we argue this? To show that we want to say that no matter what input we look at, whatever is the value that is being computed here is same as the value that is being computed here.
Yes.
Hmm. Okay, so hmm. Okay, so what is the value of G? Um, let's say, okay, how do I, okay, I think I should write more steps, no? So, okay, we want to show that G or H is same as H, and both are functions on n minus 1 variables.
Yes.
Both. Okay. So what is the value of G on a particular setting of uh, x1 to xn minus 1, it is same as the value of f on the same setting of x1 to xn minus 1, but with 0 on the nth bit.
Yes.
And what is the value of h on a particular setting of n minus 1 variables? Okay, okay, sorry, my iPad is on 3%. I'll get my charger. Okay, sorry. Yeah, so hmm. So this is yeah, we were here. So we're saying that the value of h on x1 to xn minus 1 is same as the value of f on x1 to xn minus 1 with the nth bit xn being 1.
Yes.
Okay, so so it is sufficient to show if we just by so this is nothing but for all x1 to xn minus 1 g of, we are writing the same statement but I'm writing entirely x1 to xn minus 1 or h of x1 to xn minus 1 is same as h of x1 to xn minus 1.
Yes.
For all for all substitutions. Now we will just substitute the g's and h's with the respective values in terms of f. So this is nothing but f of x1 to xn minus 1 with nth bit 0 and h of x1 to xn minus 1 with nth bit 1 is same as h of x1 to xn minus 1 and sorry f of, yeah. So just to, I'll just highlight the last bit. Okay. So this is what it boils down to.
Uh, right. Right. Right.
So in order to show this, it is sufficient to show this.
Right.
So that's why we are looking at this table. Okay, yeah, I should have yeah explained it better. So okay, so that's why we are looking at this table for f, where we have these n variables, and these are the outputs of f of x. So because f is a monotone function, okay, we know that. So this is some arbitrary setting of x1 to xn minus 1 which we are looking at, and these are the two values, right? So these values substituted with a 0 and the same values substitute appended with a 1.
Yes.
So this is the value corresponding to first one, f of x1 to xn minus 1 with the 0, f of x1 to xn minus 1 with the 1. And notice that because um, this I'll call this x, and this is our x prime. This is what we were talking earlier. So because all the other bits are the same, but in the last one the x prime is larger than the previous one.
Yes.
Okay, so what can happen is either um, I mean, it cannot be that this is a 1 but then this becomes a 0. That cannot happen because of the monotonicity property, that
Yes.
whenever x is less than equal to x prime, uh, it should have satisfy this inequality. So what are the valid options? It could be that it is 0 0 or 1 1. By 0 0 I mean this is computing a 0 and this is computing a 0. That is a valid possibility. Or this is computing a 0 but this is computing a 1, or both are computing 1. All of them are possible.
Yes.
Okay.
So you please remove this column written in the red 1 0 value showing for that
Okay.
thing. Yeah. So
Okay.
these are the possible values. It could be 0 0 or it could be
So it
uh,
could be 0 0, it could be 0 1, or
yes.
it could be 1 1.
Right, right, right.
So we want to say that in all the three possibilities, this is true.
So yeah. Um, so that would mean that let us consider the first possibility.
Hmm. Okay.
What is that? Say,
Both are
so,
0.
yes. So if
Then,
both are 0, then this would be a 0 here.
hmm,
Instead of 1 0 or 0
hmm.
is what? 0 or 0 is a 0.
I'll just copy this on the next page. Hmm. So the possibilities are, this is a 0, this is a 0, this is a 0, this is a 1, and this is a 1, this is a 1.
Yeah.
Hmm. So if we do all of these, we will get 0 here, 1 here, 1 here,
Right.
which is nothing but the same column, this value.
Yes. Oh yes, yes, yes. You're right. Yeah.
Hmm.
Fine. Yeah.
Okay, so that's why our claim that we wanted to show that G or H is nothing but H is true. Therefore, this circuit will work for us even though when xn is 1 and it is computing G or H,
Yeah.
it is still fine because that is same as H. This happened because F was monotone. If it were
Yeah.
not, then same argument falls apart.
Yes, yes.
Okay.
But this question was not easy at all. Yeah. Lots of
Okay. Okay.
tricks. Yeah.
Okay. So okay. Okay, maybe one direction was easier, the previous this direction. Um,
Yes. But then, why do we? Why are we so much interested in this monotonic functions that length or something is getting preserved
hmm.
from the computation viewpoint?
Hmm. Yeah. So, um, okay. So the one reason is that so we do know that I don't know if this was done in the class, but I mean brief overview of this thought that we know this P versus NP problem uh, is a big open problem for us, and circuits um, is one way of approaching or attacking the problem. So how is that done? So you can think of any language as a function or union of functions, right? So in
Yes.
particular, the words that we had, the P and P words, let's say L is a language in NP, then there is a corresponding union of functions that I can think of. Okay, so what we want to do is we want to separate, this is our holy grail question, whether p is equal to np, or let's say I want to separate them. Okay,
Yes.
so I know that this function is in np because I chose it that way. So how do I show that it is not uh, that np is not equal to p? It is sufficient to show that there is an l which is in np but l is not in p. So I want to show that this l is not in p. That is, in terms of Turing machine, that means there is no deterministic polynomial time machine. But in terms of circuits, we never talked about time as such. Okay, we talked about size. Okay, so there is this class called p size, which is same as p slash poly, two different classes but they happen to be the same. The definition of this class is that p size is the set of all functions such that f has a polynomial sized circuit. Okay, so this is the discussion that we had earlier, whether we know every function has a circuit, we don't know whether it is sorry, we know that some of them have polynomial size circuits, but there are functions that do not have polynomial size circuits. So this is just the collection of circuits that have poly size. And this is some other definition that I'll not get into, but you might have done this in the class if you did Karp-Lipton, right?
Yes, yes,
Huh.
yes.
And we know that p is in p size. Okay, so if I show that it's so my suffices to show that this particular language, okay, sorry, this is not I'll take click for now. Okay, I'll call this l that I'm talking about is my click problem, or the language for click. So I want to show that click is not in p. Okay, so suffices to show that click does not have polynomial sized circuits. That would mean that this click is not in p size. mm, okay, that means there is a language in np, um, okay, click, sorry, it's the other way around, p size, okay, sorry, which direction is that, okay, there is a language here which is not in p size, something called p size. So what that means is p size is which direction is that, that means np is not contained in, am I writing the right direction? Sorry, I get confused between the,
So this p-size complexity class was not covered, and because you I mean elaborated this thing in this way, so I was thinking that I mean in the case of the click, non-determinism works, but then the advice is not working. Why so? Because in the case of the p slash poly, that can be viewed as a Turing machine also, Turing machine plus some tape reserved for the advices, and the advices would be of I mean, polynomial number of the advices probably.
hmm.
So how is this happening that non-determinism is working? Click is the element of NP, and the Turing machine with an advice is not working in the case of
Ah,
the click.
okay, okay. So we don't know whether this will not work. Okay, we are just saying that this is one way, one possible attack of showing that p is not equal to np. If we knew that click is not in p slash poly, then we would be done with. We would have shown that p is not equal to np.
Oh, okay, okay, okay,
Hmm.
yes.
Okay, so yeah. So basically, what we are saying is that this problem boils down to saying that there is that this particular function, which is explicit, I mean, you know what the function is, it's a click function, does not have polynomial size circuit. So if we could show that click does not have, for example, click does not have polynomial size circuits, then there is a language which is in NP, but it is not in P size. And because it is not in P size, it cannot be in P, because P is a subset of P size.
Okay.
Okay, so that means we would have demonstrated that click is in NP, but click is not in P size. In particular, click is also not in P. That means, sorry, not in P. So that means there is a language in NP but not in P. So that would imply that P is not equal to NP.
Yes, yes, yes.
Okay,
And if
all
please, and
this.
if please, please include some right here that if condition kind of the thing, because someone who see these slides later,
Okay, okay,
yeah,
yeah.
will get
If,
it.
yeah, okay, good. If then, this is something we know.
Yes, yes.
Okay. So, yeah, so that is one approach for solving it. So what needs to be done for that is to show that click is not in P size. Hmm. So that would mean we want to show statements like, okay, no matter what polynomial size circuit we are looking at, it cannot be the same as click function. So this is like we said earlier, no, we encountered a similar statement here in the proof of this. Yeah, here, that um, no matter what, I mean, there is no monotone, there's no AND or circuit which a circuit which uses only AND or gates that computes it. So a statement like this is very hard to think of, because your argument is going across all possible circuits that are there, whereas in this case, for example, you had one circuit, there is a monotone circuit, we took that circuit and did some arguments. That is easy to do because you have that circuit. But here you are talking about all an impossibility of all possible circuits with some property, which is difficult to argue. And the same difficulty um, is something we face here, because we are saying that we want to show that no matter what polynomial size circuit you look at, it cannot compute the click function. So this is something hard to show. Okay,
Yes, yes.
and yeah, and now why we use the monotone, why we talk about the monotone circuits is because um, to make things simpler, let's say I knew there is a monotone function in NP, okay, and therefore there will be a monotone circuit for it. Hmm.
Yes.
So what I'll do is, I know that this monotone function is in NP, so this part is done. I don't need to argue across all possible circuits, but I only need to argue across all possible monotone circuits.
Right, right, right. Yes.
So yeah, so that means there could be something easier that may be there, which the general circuits don't allow us to do. So that's why this is yeah, that's one reason we study that.
Yes, yes, it's clear to me. Yeah, thanks. Yeah.
Okay, so okay, so I think I'll stop for now. There are more questions here. Um, some of them we might do it the next time, but do try it out. It will be there in the slide, the PDF that I upload. Okay.
Sure, sure. And which topics shall be covered in the next session apart from the circuit complexity?
Mm, the week 8 contents are not out, is it? Um,
Uh, week eight content. Week seven. Is until week seven.
please talk.
After.
Yeah. So
Okay.
yeah. So whatever is there in week 8, I'm also not sure. I
Okay.
don't. Yeah.
Okay. Thank you. Thank you
Okay.
so
Thank
much.
you. Yeah.
Have a good day. Bye.